Hello, everyone. Sorry, I thought my voice was lost during the middle of the introduction. So I assume that you can hear me right now, right?
Yes.
Okay. So I guess, yeah, I think people may miss a part of my introduction, but you heard me at the beginning, right? When I
Yes.
started
I
talking.
lost you at the questions.
All right. Okay. Anyway, yeah. So I introduced to Dr. Mehmet Yildirimoglu, and I think I'm not going to do that again due to the time. So his information presentation topic is available in the flyer. Um, I guess we're going to have a question and answer sessions by the end. I'm going to remind you, but without further ado, I would like to um, give this presentation to Mehmet, and welcome, Mehmet.
Okay. Thank you for the introduction. My name is Mehmet Yildirimoglu. I'm a postdoc at Urban Transportation Systems Laboratory at EPFL Switzerland. This is a joint work we have done with Mohsen Ramazani, who is currently in Monash University, and Nicholas Geroliminis. The title of our work is Equilibrium Analysis and Route Guidance in Large-Scale Networks with MFD Dynamics. We mainly have two purposes in this work. The first one is to investigate the effects of different traffic assignment techniques on Macroscopic Fundamental Diagram. There are a few studies that are based on real data, but most of MFD estimations are based on microsimulations where driver adaptivity is incorporated by in-route decision mechanisms. That means vehicles choose the shortest path based on instantaneous travel times and update their decision with a certain frequency. Our purpose here is to establish user equilibrium and system optimum conditions in a lower layer model and observe the effects on the resulting macroscopic fundamental diagram. The second purpose is to develop a route guidance system and improve the traffic conditions. And the main difference of this work from other route guidance studies is that we have an aggregated model, but travelers still need detailed routing information. In order to highlight this difference, we have created two traffic models with different aggregation levels, and we transfer certain parameters between them with a rolling horizon. This is the outline I'm going to follow today. I will start with a quick background check. I will describe macroscopic fundamental diagram, and I will talk about what equilibrium means in an aggregated framework. Then I will continue with methodology. I will describe two traffic models that we have created, a plant which represents the reality, and a model where we produce the route guidance information. Then I will continue with the framework of route guidance system. There we have two modules, stochastic network loading, where we take care of stochastic components in the model, and method of successive averages. It's a fixed point solution heuristics when the derivative information is difficult to be calculated. Then I will finish my talk with results. I will present you the system performance under different assignment scenarios. And I will finish my talk with discussing equilibrium effects on MFDs. Let me quickly describe what macroscopic fundamental diagram is. Here we have a fundamental diagram from an individual detector in the urban network of Yokohama. The relationship between flow and density is quite scattered here, and it doesn't tell us much about the traffic conditions. But when we collect the same type of information, flow and density, from many detectors in the same urban area and calculate the average flow and average density, we observe this well-defined relationship that we call macroscopic fundamental diagram. This relationship is unimodal. It only has one maximum point, and this is quite useful when we want to develop macro-scale traffic management strategies. It has low scatter. That means the model is quite accurate. And most importantly, it is demand insensitive. Here we have points from different time periods in a day with different demand profiles, yet they all fit on the same curve, which means we have a demand insensitive relationship. Unfortunately, Definitely, this is not a universal law. When the network is big and heterogeneous, we start observing more and more scatter, and we start losing the well-defined relationship. In this case, we need to partition the network into smaller homogeneous areas where we still have valid MFD functions. This figure here is from a previously developed partitioning algorithm. Here we have the link density distribution. The darker the color, the more congested the link is. With this link density distribution, the algorithm returns 3 homogeneous areas where we still have valid MFD functions. Another interesting thing here is that all these 3 regions reach the critical accumulation or the congested regime at different time periods. That means they have different loading patterns. Actually, the partitioning results will be enough if you would like to develop a responsive control strategy. But traffic often requires us to be proactive. That means we should be exploring the prediction power of such traffic models. Imagine that you apply the partitioning algorithm at a city scale, and these are the partitions you end up with. What we notice here is that there is actually more than one way of going from one region to another. That means people have route choices even at the regional context. And in order to predict traffic conditions with such a model, we need to understand how people make choices in this framework. And we need to develop a traffic assignment model that can deal with the characteristics of our model. We know that depending on the exact location of origin and destination points, people can make different regional route choices. And our algorithm will take care of this through a sampling procedure. Like I said in the beginning, we are also interested in the shape of MFD with equilibrium scenarios. Here I have 2 MFDs that are based on real data and one which is based on simulated data. In the network of Yokohama, in both loading and unloading phases, we see that all points fall on the same curve. In Toulouse, we have a similar phenomena for the 2 of the days that are analyzed here. But for a 3rd day, we see that the network comes back to the free flow state from a complete different line. This is what we call hysteresis. But we know that for this specific day, there was a protest of truck drivers in the city, which caused completely unexpected traffic conditions, and we cannot talk about equilibrium anymore. The last example is from the simulated network of Chicago. This is based on a simulation where driver adaptivity is incorporated by en-route decision mechanisms, so we cannot talk about equilibrium, and the effect of hysteresis is even more obvious here. So all these results here make us think that equilibrium might have something to do with the existence of hysteresis, and this is what we are going to investigate in this work. Before going into details of the traffic models we have developed, I would like to briefly talk about how we can calculate outflow with MFD approach. MFD is, like I said, MFD is the relationship between average flow and average density, and these are just proxies for production and accumulation in a region. If you know the production in a region, and if you know that the average trip length is constant throughout the day, like in the case of Yokohama, you can simply use this formula to calculate the outflow from region R at time t. Keeping this formula in mind, I will go for more complicated traffic models. Like I said in the beginning, the main difference of this work from other route guidance studies is that we have an aggregated model, but travelers still need detailed routing information. So to highlight this difference, we have created 2 traffic models with different aggregation levels. Plant or sub-region based model represents the reality. It's quite detailed, and it has 19 sub-regions. The operation model or region-based model is the model where we produce the routing information. It has 3 regions which consist of several sub-regions. Ideally, plant should be the reality or a detailed macroscopic simulation model, but for practical reasons here, we create 2 traffic models that are based on MFD equations. But the aggregation level is quite different between these 2. Here's the list of variables we use in the plant and in the model. The main difference between them is how we define accumulation, or the state variable. In order to run a traffic flow model in the plant, we need to know the whole path between origin and destination. And we define the accumulation in region R separately for each OD pair and the chosen path. This type of information, from a model point of view, we assume that this type of information is not available to us. So we define the accumulation in a much simpler way. We define the accumulation in region I for each destination region J. Another major difference between these two is the average trip length. In the plant, we assume we have constant average trip length, while in the model, we allow for dynamic time-dependent average trip length between region I and neighboring region H. So now we can take a look at how we calculate the outflow in the plant and in the model. In the plant, we calculate the outflow at each little boundary between the subregions. And this is the formula we use for that. Actually, this is very similar to what I have shown before. But right now, we calculate the outflow for a specific group of travelers in region R. So we need to multiply this term by the fraction of that group. In the model, we calculate the outflow at large boundaries between the regions. This is the production. We divide it by time-dependent average trip length. And in order to run a traffic flow model, and in order to propagate the flow, we need to know the proportion of accumulation which chooses next region H. In this work, we propose several assignment scenarios. In the plant, we are going to establish user equilibrium and system optimum conditions. And there we are going to use only the plant dynamics, and we will assume complete information of traffic state in the plant. Here, user equilibrium will represent the base scenario that we want to improve, and system optimum scenario will represent the upper bound for improvement with routing. The third scenario is route guidance. This will be based on system optimum conditions in the plant. But this information, these conditions will be transferred to the plant through a rolling horizon, and it will be tested there. The main challenge in this work is that route choice variables that yield equilibrium conditions in the plant and in the model, they are quite different from each other. In the plant, we use the path fractions between OD pairs, while in the model, we use split ratios and average trip lengths. So the challenge here is to translate this information to the plant language and test it there. I'm not going to talk about how we reach user equilibrium and system optimum conditions in the plant, because this is rather straightforward. Simply over the iterations, we update path fractions between ODs, and we hope to reach equilibrium conditions. I will continue with the route guidance framework. There we mainly have two modules, stochastic network loading and method of successive averages. Stochastic network loading consists of a sampling procedure. It works in a Monte Carlo fashion. Method of successive averages is a fixed point solution heuristics. It becomes very useful when the derivative information is difficult to be calculated, and it helps us reach the fixed point solution. Before going into details of these two modules, I will like to simply briefly talk about the rolling horizon method. In the beginning of a time step, at time t0, we need to extract the true variables from the plant and correct our variables. What are these variables? These are average trip lengths, split ratios, and regional accumulations. Once we have these variables, we can go and play with the route choice variables over the projection horizon. These are namely L's and theta's, and we play with these variables within the projection horizon between time t0 and t0 plus tp, which is the length of the projection horizon. And once we reach equilibrium conditions, we return the path fractions between origin destination pairs, and we test this information in the plant by running the plant only for one time period. And in the next time period, we repeat the whole procedure again. This is a quick example about how we can calculate average trip length in the network. I will not go into details of this formula, but simply what we are doing here is regrouping the variables in the plant in a way that we create region-based variables. And here we are simply rewriting the outflow formula to calculate the average trip length. Now I would like to continue with stochastic loading. The purpose of this step is to calculate average splits and average trip lengths in response to some given traffic conditions. We know that origin and destination points are randomly distributed around the network. In order to calculate these average values, we follow a sampling procedure, a Monte Carlo simulation procedure, if you like, and we sample an origin destination point. Then we determine the shortest path between these origin destination points, which is based on marginal travel time. Here we use marginal travel time because our purpose is to reach system optimum conditions and improve the network performance. But when we do this, we do not assume we have full information from all the links in the network. What we have is accumulations in all the regions, so we can calculate the average traffic conditions. And by assuming all links in the same region have the same speed, we can determine the shortest path between point O and B. Once we have this trajectory, we cut it at the boundary intersection points. This way we will be able to calculate the contribution of this trajectory to different regional variables. Let's start with the contribution to average split ratios. In the beginning, the trajectory is in region I. Destination region is N, and the next region is K. So firstly, it contributes to theta INK. Once it is in region K, the current region becomes K, destination region is always N, and next region becomes N. So it contributes to this variable. And in the last region, all current region, destination region, and next region become N, and it contributes to this variable. We apply the same idea for the average trip lengths, but this time the contribution will be weighted by the distance that is crossed in the corresponding region. And we don't have the destination information here. We only use current region and the next region. We do the same for all different regions. And we apply this procedure for as many OD pairs as needed for convergence. And at the end of the procedure, we calculate the average split ratios and average trip lengths. Now we can take a look at the overall algorithm. We start with some time-dependent region speeds. We go and apply the stochastic loading method, and this way we calculate thetas and L's. In order to smooth our results and reach equilibrium conditions, we apply the famous formula of MSA, and we update our variables, our decision variables, with a predetermined step size of 1 over m. Once we have these new variables, we go and plug them into our region-based model, and we produce new time-dependent region speeds. And we apply this procedure again and again until we reach a fixed point solution where any of these variables doesn't change significantly. Once we have the equilibrium conditions, we return the stored paths between sampled ODs at time t0, and we run the plant with these path fractions for one time step. And at the beginning of the next time step, we repeat the whole rolling horizon procedure again. Here I have the results with different assignment scenarios and with different demand levels. User equilibrium here again represents the base scenario that we would like to improve. System optimum is the upper bound for improvement with routing. And with route guidance, we would like to be as close as possible to the system optimum conditions. And actually, this works pretty well for almost all demand scenarios except the very high demand scenario. And there what happens is the network is so congested that our assumption about the homogeneity, about the average traffic conditions doesn't hold, and we fail to keep track of traffic conditions. But to be fair, this scenario here is quite congested. The system goes to gridlock, and it's not very realistic. But our model works pretty well with all moderate congestion scenarios. Like I said in the beginning, we are also interested in the shape of MFD with equilibrium scenarios. Here I have MFD functions for 3 regions that I mentioned before. The black one is the inner region, which is more congested than the rest. And blue and red ones are the regions at the periphery. As you can see here, although the inner region is quite congested, in any of the equilibrium scenario, it doesn't suffer from the hysteresis. It comes back from the same line. We tested the same scenario with an in-route assignment strategy. Their vehicles take decisions based on instantaneous travel times, and they update their decisions with a certain frequency. And as you can see here, we have a significant hysteresis here in the inner region. In addition to this, the regions at the periphery, the blue and the red curve here, suffer from a mild hysteresis. And this is due to the artificial network structure we create. If you take a closer look here, the regions, the subregions with an odd number are connected to 3 neighboring subregions. But subregions that have an even number are connected to 4 neighboring subregions. And this creates some imbalance between the accumulation distribution among the subregions at the periphery. And this is the reason of mild hysteresis here. So all these results allow us to say that equilibrium has something to do with the existence of hysteresis and homogeneity of the network, but network topology has an effect as well. This is my last slide. I would like to show you a short video about the distribution of congestion in the network. Here we have user equilibrium, system optimum, and route guidance scenario, and you will see how the congestion is distributed among the subregions. In user equilibrium scenario, we see that the inner part of the network is much more congested than the periphery, while in system optimum and route guidance scenarios, we are able to properly distribute the congestion and finish the congested period much earlier. This way we can improve the traffic conditions. Okay. With this, I would like to finish my presentation, and I will be happy to answer your questions if you have any.
Thank you, Mehmet. Very interesting presentation. At this time, I think we're open up for questions from the audience. You can, I think I would just recommend you unmute yourself and speak out, and this may be more interactive. Or if you want to take some time to organize your words, or you're just simply shy, you can use the chat box. And there is a chat box on the control panel on this control console. This chat box is actually, I believe, is one of the lowest boxes on the console. And so when you send out your chat message, please make sure that you send it to organizers and panelists only. Again, organizers and panelists only. This is just how the system is set. You know, in order to reach all the audience, we have to do that. But of course, I would just rather like you to unmute yourself and speak out if you want. Okay, is there any questions?
Yes. Hi.
Hi.
Can you hear me?
Yes, we can.
Sure. Great presentations. Thank you. I'm Frank. I'm from Monash University. So indeed, I'm working quite closely with Mosen, which is one of the authors on the first slide. So yeah. Anyway, I was wondering, because you said that there are 3 scenarios which are user equilibrium, system analysis, system optimism, and route guidance. I'm familiar with user equilibrium and system optimism. So could you explain a little bit more about route guidance? What is the difference between route guidance and the other 2 scenarios?
Okay, so in user equilibrium and system optimum, we assume we have complete information about the traffic state. What I mean by traffic state is the exact accumulation in all the subregions. And over the iterations, we update the path fractions that OD pairs are choosing, and this way we reach equilibrium conditions. While in root guidance scenario, we don't have the subregion accumulations. We only have regional variables, regional accumulations, average trip lengths, and split ratios. So in a way, we assume that some part of the reality is not observable to us, and we try to improve traffic conditions with a model which doesn't perfectly represent the reality. That is the main difference between them.
Okay, thank you. So, yeah. So, because you also talked about stochastic network loading, so I was wondering if this technique is only used in root guidance, or it is used in all the three scenarios.
Oh, okay. So in user equilibrium and system optimum, it's not exactly like stochastic loading because we know exactly where the demand is, and we do this for all origin-destination pairs. In the root guidance scenario, we assume we have the distribution and we sample from this distribution.
Okay, right. Thanks. So, are all these scenarios implemented in a dynamic environment?
Yes, they are all dynamic. Yes.
So you do have like a multiple OD demand, or am I right?
Yes.
Okay.
It's a time-dependent OD demand for all the pairs we have in the network.
Okay, right. So, sorry, a final question. So how long did you simulate for all these scenarios? I mean, is it 1 hour or 2 hours?
No, it doesn't take that long, but I'm not sure how long it was taking. So
okay.
the problem.
Sorry. I don't mean about the simulation time. I just want to. I just wondering. Because you said that there are multiple OD demands, so I was asking, you know, how long was this OD demand?
Oh, okay, I see. I think the simulation time is 2 hours.
Okay. Thank you. Yeah, that's all. Thank you. Great presentations again.
Thank you.
Yeah.
Thank you. Any other question?
Hey, Mehmet, and I would like to ask a question for Dr. Jack Haddad from Israel Institute of Technology, and he's driving, so he, wanted me to ask this question.
Okay.
So he first said, very nice presentation. His question is that, do you have any future research plan related to combined framework with route guidance or parameter control?
Yes, that's part of my future plan, but right now I'm working on the route guidance problem, looking at it from another way. Basically, what we want to improve here, what we want to optimize here is thetas, the split ratios. So what we are planning to do is we are planning to put the whole model into an optimization framework and optimize thetas. And when we go back to the detailed model, to the plant, we are going to run a distribution model which is based on mixed integer linear programming, and we are going to distribute these thetas among the subregions in a way that we satisfy the split ratios and average trip lengths. So right now, the algorithm works in an iterative way, and it goes back and forth between the plant and the model. So what we plan to do will be a bit different. We are going to optimize the thetas within the optimization framework, and we are going to distribute it in the plant using another optimization framework which is based on MILP. Another future direction, as you mentioned, is to combine this with a perimeter control strategy. And actually, this is one of the things we have tested before. And one problem we run into is that perimeter control and route guidance are competing with each other. So what I'm trying to say is, for example, perimeter control, you apply perimeter control in this scenario, and you try to protect the inner region, because apparently it is more congested than the rest. But when this happens, route guidance scenario will try to push the vehicles to the inner region, because the algorithm knows that it is less congested than the rest, because perimeter control is trying to protect that area. So there is this problem of competition, and we couldn't find the perfect way to deal with this problem yet, but definitely this is something which is in my future agenda.
Great, thank you. I think Jack has heard about your answer. That's great. Any other questions? Oh, yeah, he said that this competition makes the problem interesting. Yeah, so looks like this is very promising future research direction, and yeah, from Jack. Any other questions from the audience?
I guess that's it.
Okay, looks like yeah, we're almost there. Thank you, Mehmet, for your nice presentation and interesting work. So I wonder, would you mind sending us this set of slides? It's up to you. All right, if you can forward it to me, and I'll be able to upload it together with the video.
Okay.
Oh, that's great. And thank all of you for dialing in and attending this seminar. Excuse me. And I really appreciate it. So I guess this is one of the last presentations we have for the ISTTT series, if not the last. So we're still trying to confirm with some other speakers. So the next one hasn't been scheduled, but anyway, I appreciate all your support, and it's a great experience with all of you. So hope you have a great weekend and wonderful summer. With this, bye-bye.
Thank you. Bye.
Bye.